In section 2.4, we turn our attention to graphs of functions. So one of the main features of a function is its graph, and actually the graph can help us really understand what the function is representing. So let's remember that if we are given a value for x, which is the independent variable, then f of x, which is the dependent variable, is the output value of the function. In the xy plane, the input value x is the x coordinate, and the output value f of x is the y coordinate. Remember in the last section I told you that f of x is just another name for y. The graph of f is the set of all points x f of x such that x is in the domain of the function. All right, so we're just going to start with a simple example here. Suppose I give you the set of points s equals -1, 0, 0, 1, 2, and 2, 4. Does this define a function? It's a little bit hard to tell when it's written like this, but if we take these x and y values and write them in a column, you can see that basically this is a function because no one x value goes to more than one y value. In fact, every single different x value goes to a single y value. Now, we can also graph this, and all we have to do here is put these points in a coordinate system. So the point -1, -1 is this point right here. The point 0, 0 is this point. The point 1, 2 is here. And the point 2, 4 is here. And you can see that every single x value, right, the x values are -1, 0, 1, and 2, goes to a single y value. So yes, this set of points represents a function. Now let's focus on an example that is a little more common. Here they want us to graph the function f of x equals 2/3 times x minus 2. Now let's keep in mind that the domain for this function is the set of all real numbers. So it's -infinity to infinity. So you are free to plug in any value you want for x. Positive, negative, fraction, decimal, doesn't matter. You can plug in anything you want. Now, what we're going to do is plug in a few values of x, and you can see that I stole this from the book here. We have these 5 values for x that we are plugging in. When we plug those values in, we're going to get the value of y that corresponds to those values of x, and then we will graph those points. So just to make sure you understand what happened here, let me just pick the first number. How do I know if x is -6? How do I know that f of x is also -6? Well, what we do there is we plug -6 into the function. So f of -6 means that we are going to take the number -6 and we're going to replace x with that number. So when we do that, we get 2/3 times -6 minus 2. And now what happens here is you can think of -6 as being -6 over 1. And 3 goes into 6 2 times. So what you have left over here is 2 times -2. And that is -4, and then minus 2. And -4 minus 2 is -6. Okay? Now, just to make sure we totally understand this, let's plug in one more value from this table. Let's plug in x equals 3. So if I plug in x equals 3, we're doing f of 3. According to the definition of the function, that will be 2/3 times 3 minus 2. This one's even nicer because the 3's cancel each other out. And what we're left with here is 2 minus 2, and 2 minus 2 is 0. And you can see that's how they got the value over here. So if you do that to all of these values here, you get these values over here. All right. So what does that mean in terms of the graph? Well, if I graph every single one of these points, my first point is -6, -6, which is this point right here, right? X equals -6, y equals -6. My next point is -3, -4, which is here. Then we have 0, -2, which is here. And then 3, 0, which is here. And finally 6, 2, which is here. And you'll notice that all those points line up to make a straight line. So when we graph this line, when we draw the line connecting all of these points, you need to understand that what you're doing there is you're showing what all the other points would look like if you had plugged in all the real values for x. So remember in the beginning, we said the domain for this function is all real numbers. Well, it's impossible to plug in every single number into a function. So what we do is we plug in a few numbers. In this case, we plugged in 5 numbers. That gave us 5 points. And what we hope to see is some kind of a pattern with those 5 points. And of course, the pattern here is very simple. It's a line, okay? But that's essentially what we're doing. So when we connect all these points, we're representing all of the other points on the graph. So just as a quick example, what if I had chosen x equals 1? If I had chosen x equals 1, f of 1 would have been 2/3 times 1 minus 2. 2/3 times 1 is 2/3. 2/3 take away 2 is -4/3, or -1 and 1/3. That point is somewhere on that line. Let's find it. So when I plug in x equals 1 is right here on the graph. If I go to the graph, you'll see that the corresponding point is right there. That point has an x-coordinate of 1, and the y-coordinate is this coordinate right here, which is -1 and 1/3, okay? So even though we didn't pick x equals 1 initially, you'll notice that when you connect the dots on this graph, you're getting not only the points that you chose, but you're getting all other points that you could have chosen, all right? So every x and y value that satisfies this equation is a point somewhere on this line, and every point on this line has to satisfy this equation. That's the relationship. So this next example is very similar. We want to graph the function g of t equals -2t squared. And again, I got this table from the book here. You can see that they have chosen these 5 values for t, and they get these 5 values for g of t. Now, let's just make sure that we understand where those values are coming from. So for example, when t equals -2, g of -2 is, according to the function, which is right here, it is -2 times the value of t quantity squared. So that's going to be -2 times the value of t, which is also -2 to the second power. And this means -2 times, -2 squared is 4, right? Because -2 squared means -2 times -2, which is 4. So in the end, we get -2 times 4, which is -8. Okay, and again, remember your order of operation here. You have to do exponents before you multiply, okay? So that's how they got the value of -8 here, and you could plug the rest of these numbers in to get the rest of these values. Okay, now, what does that mean in terms of the graph? Well, if you take all of those numbers that we get here, all these points, and you plot the points on the graph, so -2, -8 is here, -1, -2 is here, 0, 0, +1, -2 is here, and +2, -8 is here. And when you plot those points, you can see that we get this sort of upside down U-shaped graph, which we call a parabola. Now, it also says use the graph to find the domain and range of the function g. So let's talk about that. The domain is the set of all of the values of t that you are allowed to plug into the function. So let's think about this. From an algebraic point of view, you can see that you can plug in any value of t that you want. So your domain is going to be all real numbers. Now, again, that's because you never have to worry about dividing by 0 or taking the square root of a negative or anything that is restricted, right? Now, another way to interpret this is notice that the graph covers every single value on the t-axis here, right? So when t equals 2, we get a value for that. When t equals 3, we get a value for that as well. It would be farther down here, but eventually you're going to get a value for that. And no matter what value of t you choose, there is a value of g of t on this graph. So the domain is all real numbers. Now the range is trickier. Remember, the range is the set of output values. Look at your output values. Look at your graph. In terms of the output values, which are the values on the y-axis, you can see that you don't get any output values up here, right? There's no graph that is anywhere up here. So all of your output values are down here. They are at 0 or below 0. And you can see that in your table. All of your output values are negative except for the one in the middle, which has an output value of 0. So for your output values, which is your range, you do not get any positive numbers. You get starting at 0 going to, you get starting at negative infinity going up to 0. Okay, so your range is from negative infinity to 0. Let's do a couple more examples just to make sure we understand the concept. So in this next one, we want to graph the function f of x equals the square root of 4 minus x. I'm going to do this one by making a table of values. We'll do it ourselves here. So I'm going to make a table of x values, and then we will get f of x values. And we talked about this function in the last section. You can plug in x equals 4, but you cannot plug in anything greater than 4. If you do, 4 minus that number will be negative, and then you will have the square root of a negative, which is an imaginary number, right? So I can plug in x equals 4, I can plug in x equals 3, I can plug in 0, I can plug in negative 5, and yes, I'm picking specific values of x. Okay, let's plug these in to see what we get. So when you plug in 4, you get the square root of 4 minus 4, which is the square root of 0, which is 0. When you plug in 3, you get the square root of 4 minus 3, which is the square root of 1, which is 1. When you plug in 0, you get the square root of 4 minus 0, which is the square root of 4, which is 2. And when you plug in negative 5, you get the square root of 4 take away negative 5, which is the square root of 4 plus 5, which is radical 9, or 3. So you'll notice that I picked values of x that end up giving me nice square roots. Now, I do this because I have a lot of experience, but with experience, you'll also be able to kind of select good values of x that will give you nice y values. Now, if you had picked something that was maybe not quite so nice, like maybe you picked x equals negative 2, for example, then you would get the square root of 4 minus negative 2, which would be the square root of 6. And then to graph that point, you would have to plug that into a calculator, right? So we would need to know, like, how big is the square root of 6? So if you plug that into a calculator, you'll find out that it's like about 2.4. And then you could use that to help sketch your graph. Okay, but it's a lot easier if you just pick values that give you nice numbers. And that will come with experience. So now let's go ahead and sketch a graph here. So starting with the first point, we have the point 4, 0, which is right there. Then we have the point x equals 3, y equals 1. And then the point x equals 0, y equals 2. And finally, we have the point x equals negative 5 and y equals 3. And just for good measure, x equals negative 2, y equals 2.4 would have been right about there. And you can see that when you connect the dots on these, you get sort of a curved function that looks something like this. Okay, so that is the graph of the function. Now what we want to do with this is we want to use that graph to find the domain and the range. So let's remember that the domain is the set of x values, and the range is the set of y values. Now, for the set of x values, look along the x-axis. Every x value that has a graph associated with it, so every x value that has a graph above it, will be a value that's in the domain. So we can see all of these values here going forever to the left. They all have a graph. But then when you get up to x equals 4, that's where the graph stops. So you do not have a value for x equals any number larger than 4. So our domain is from negative infinity up to 4, including the 4. Okay? So literally you're just looking at like what values of x on the x-axis there are covered by that function. Okay, and you can see it's all these values here from minus infinity all the way up to 4. All right, so that's how we can picture it. Now, if we do the range is the same concept, except that we're going to look at the y-axis. So when you look at the y-axis, which is here, we want to see what are the y values that have a graph associated with it. Well, as you can see, there's no graph anywhere down here. So none of the negative y values have a graph associated with it. The first y value is y equals 0, which is right here. And then you can see that the graph goes up from there. So every y value above 0 is going to have a graph associated with it. So your range starts at y equals 0 and goes to positive infinity. Now, just for kicks, I'll bring in an image from the textbook, which kind of shows this a little bit better. So here you can see we have the graph of our function, which is right here. The domain is all of these values here on the x-axis, right? So that's all the values from 4 over here all the way to negative infinity. But of course, the way we say that is we go from negative infinity up to 4. And then the range, you can see that these are all the values covered by the function on the y-axis, and those start at 0 and go to positive infinity. So our range goes from 0 to positive infinity. All right? Okay, let's take a look at the other problem here. So for part B, we want to graph the function f of x equals the absolute value of x. So for this, we'll do the same thing. We'll make a little table of values here, x and f of x. And I'm just going to pick some standard values like x equals 2, x equals 1, 0, negative 1, negative 2. And absolute value is pretty simple. When you take the absolute value of number, you just give the distance that number is from 0. So the absolute value of 2 is 2, absolute value of 1 is 1, absolute value of 0 is 0. Absolute value of negative 1 is positive 1, and the absolute value of negative 2 is 2. So if I sketch these points, we have the point 2, 2, 1, 1, 0, 0, negative 1, positive 1, and negative 2, positive 2. And if I connect here, you can see that we have this graph. Okay, and now we can talk about what is the domain and what is the range. Well, again, the domain is all of the x values that are covered by this graph. So you should be able to see the domain is all real numbers. And the range is the set of y values covered by this graph. And you can see once again here, the y values are only up here. There is no graph down here. So none of these negative y values are covered by the graph. So again, it starts at 0 and it goes up forever. So the range would be from 0 to infinity. Next, we're going to talk a little bit more about graphing piecewise defined functions. So to graph a piecewise defined function, the key here is you need to graph the function in pieces. So For example, if I want to graph the function h of x is equal to x squared if x is less than 0, x plus 1 if x is in between 0 and 3, including 0, or h of x is negative 1 if x is greater than or equal to 3. So to graph that, what I'm going to do is graph it in 3 pieces. So first of all, I'm going to focus on h of x is equal to x squared. Now, I will only do this if x is less than 0. So what that means is that I'm going to make a table of values, and in this table, I can only pick negative numbers, right? Because I can only pick values of x that are less than 0. So for example, I can pick x equals, negative 3, negative 2, negative 1. I could even do something like negative 1/2. Okay, and I just got to plug those values in. For the next piece, I'm going to be graphing h of x equals x plus 1, and I'll do that if x is between 0 and 3, including 0 but not including 3. So again, when I make my table of values here, I can include 0, and I'm going to go all the way up to 3, but I can't include 3. So maybe I'll go to 2.5 or something like that, okay? You can go closer if you want. You can plug in 2.9, all right? But I can't go all the way to 3 because 3 is not included. And for the last piece, we have h of x is negative 1, and this is valid if x is greater than or equal to 3. So for this one, I can plug in 3 or higher. So I'll plug in the values x equals 3, 4, and 5. Now what I need to do is actually plug these values in. And I won't show all the work here. I'll just verbally go over it. So for example, here, when you plug in negative 3 to the second power is negative 3 times negative 3, which is positive 9. Negative 2 to the second power is positive 4. Negative 1 to the second power is 1. And negative 1/2 to the second power is going to be negative 1/2 times negative 1/2, which is positive 1/4. Okay, and I'll plot those in just a second here. Let's go ahead and plug in our values from the next table, and these will be plugged into the function x plus 1. So when x is 0, 0 plus 1 is 1. When x is 1, 1 plus 1 is 2. When x is 2, 2 plus 1 is 3. 2.5 plus 1 is 3.5, and 2.9 plus 1 is 3.9. And finally, for the last piece, and this is the easiest piece, h of x is negative 1 for all values of x greater than or equal to 3. So it doesn't matter what x is, the y value here is always negative 1. Now let's see what this looks like. So we had the point negative 3, negative 9, which is kind of far off of our chart here. That's a little bit too far down to graph. But our next value is negative 2, 4, which is here. Then we have negative 1, positive 1, which is here. And then we have x equals 1/2 and y equals 1/4, which is right about there. Okay. And then for the next piece, we have these points. So we have the point 0, 1. Let me do it in a different color. Let's use green for that. So 0, 1. Then we have 1, 2, 2, 3, 2.5, which is right here, 3.5, 2.9, and 3.9, which is like this. Okay, and that's all we got there. And then for the last piece, which I'll do in black, we have the point 3, negative 1, 4, negative 1, 5, negative 1, and this continues. So this last piece looks like this, okay? The piece in the middle, if I connect these points, you'll notice that it's going up, 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 getting closer and closer to this point here, but I have to put a circle there because remember, at 3, we cannot actually plug in that number. Now let's pretend for a minute. If we did plug in 3, 3 plus 1 would have been 4. Okay, so that's that point right there. That is the point 3, 4. But I have to keep it hollow because we can't actually plug in 3, right? Because it's not included, okay? And for the first piece of the graph that we got, you can see that if you connect these points, it looks something like this, and it's coming down, 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 and we're wondering, well, where would that one have gone? Well, again, technically we're not allowed to plug in 0, but if we plug in 0 anyway, 0 squared would have been 0. So 0, 0 is this point right here, but it has to be an open circle because, again, that point is not included. So what you get in the end is you get a graph that is composed of different pieces. Okay, so this piece of the graph represents the first part of the piecewise function. This piece of the graph represents the second part. And finally, this part represents the last part. So I don't think that piecewise graphs are really terribly difficult to do, but you have to be patient and you have to go slowly enough to make sure that you don't make any errors. Now let's talk about something called the vertical line test for functions. This is a really simple test that you can apply to a graph to see if the graph represents a function. So you can read this here if you want, but basically it goes like this. If you have a graph and you want to know if the graph represents a function, simply imagine every possible vertical line that you could draw. If the graph is a function, every possible vertical line will only hit the graph at the most one time. Okay, so you can imagine that if I were to graph more vertical lines, every possible vertical line that I could graph would only hit the graph one time. Okay, so this graph that you see right here, this graph does represent a function because every possible vertical line only hits the graph once. Let's take a look at some other examples. So in these three, we want to use the vertical line test to determine which of these graphs are graphs of functions. So what I like to do is just take my graph, so we'll take this first one here, and I'll just kind of like graph a whole bunch of vertical lines, and I'll say, if I keep graphing every possible vertical line, do any of those vertical lines hit the graph more than once? And the answer here is no. Every single line that I drew only hits the graph one time. So yes, this graph is a function. Now, if you look at the next graph, you can see pretty clearly right away this is not a function, because if I draw a vertical line here, notice that it hits the graph twice. If I draw a vertical line here, notice that it hits the graph 4 times, right? And if I draw a vertical line over here again, you can see it again, it hits the graph twice. If any vertical line hits the graph more than once, it is not a function. So this one is not a function. And finally, for our last graph here, is this a function? Well, you can see that if we draw a line here, anywhere in here, all these lines are only hitting the graph one time. If you draw a line over here, it doesn't hit the graph at all. That's okay. It doesn't have to intersect the graph at all, but if it does intersect the graph, it can only hit the graph once. So yes, this is also a function. So the first and last ones are functions. The middle one is not a function according to the vertical line test. One more thing I want to talk about is something that is called intercepts and also zeros of functions. This is really important. When graphing a function, it is important to know where the graph crosses the x and y axes. An X-intercept is a point where the graph of the function crosses the x-axis. In terms of function terminology, the first coordinate of an X-intercept is the value of x such that f of x is equal to 0. Let's think about that for just a second. So you can see on this graph right here, here is a point. This point is the point 2, 0. And you can see that it crosses the x-axis at that point. At that point, notice that x is equal to 2 And notice that y, or f of x, is equal to 0, okay? So when we're talking about an x-intercept, it is the same to say x-intercept or to say f of x is equal to 0. Okay, so x-intercept and f of x equals 0, these mean the same thing. All right? Okay. The second coordinate of the x-intercept is 0, and that's that part where we say f of x is 0. The values of x satisfying f of x equals 0 is called the zeros of the function. Okay, so we just said an x-intercept is the same as f of x equals 0, and now they're saying those values of x that make f of x equal to 0, those are called the zeros of the function. So x-intercept, f of x equals 0, and zeros of the function f of x, these all mean exactly the same thing. So we need to get used to that terminology. So if I ask you, find the zeros of the function, or if I say, find the x-intercepts of the function, or if I say, when is f of x equal to 0? All three of those questions are exactly the same question. All right, now let's talk about the y-intercepts. The y-intercept is a point on the graph where the function crosses the y-axis. So for example, this point right here. This point is the y-intercept because you can see that's where it crosses the y-axis. Notice that the coordinates for your y-intercept is x equals 0, and then in this case, y equals 3/2. The 3/2 represents where on the y-axis does it cross. For a y-intercept, x is always going to equal 0, okay? So when you are looking for a y-intercept, you simply let x equal 0 to find the y-intercept. That's the method that we use for finding it. And the other thing to keep in mind, this last little part here, is graphs of functions do not always have to have an x or a y-intercept. Okay, most functions do, but they don't have to. All right, now let's really look at this example here in a little bit of detail. So it says, consider the graph of the function f given here. The questions down below here are to find f of -1, f of 0, and f of 2. Now we're going to do this by looking at the graph. So to find f of -1, I'm going to locate -1 on the x-axis, and I'm going to go to the function, and then I'm going to observe what is the y value there at that point. Well, it's kind of hard to tell when you look at the y-axis, but they actually gave us this point right here. And they say when x is -1, y is 1/2, okay? So from that, we can answer the question, f of -1 is 1/2. Now let's find f of 0. To get f of 0, we do the same thing. We go to 0 on the x-axis. We go up to the function, which is right here. And again, you can't really tell by looking at the graph where exactly that point is, but they tell us right here when x equals 0, y equals 3/2. So f of 0 is equal to 3/2. And finally, to find f of 2, we do the same thing. I'm going to go to 2, which is right here. And you'll notice that f of 2 is actually right there on the x-axis. And they give the coordinates of that point as well. F of 2 has to be 0, right? Because the y value there is 0. So a couple of things to note, and we'll talk about this actually in part C, but f of 0 equals 3/2. This is our y-intercept, isn't it? Because that is where the graph crosses the y-axis. And then f of 2 is equal to 0. This is one of our x-intercepts because that is one of the points where the graph crosses the x-axis. Okay? All right, we'll talk more about that in part C. In part B, it asks to find the domain of the function. Well, if you look at the function, the domain is a set of all real numbers because all these values of x have a y value associated. And you can imagine as this function continues to go down here, it also continues to go out. So every value of x you can think of is going to have a value of y associated with it. So the domain of the function is minus infinity to infinity. Now finally, in part C, what are the x and y intercepts of the graph of f? So we already mentioned it a little bit before, but the x-intercepts is going to be all the numbers where it crosses the x-axis. So that's going to be this point right here and this point right here. So as points, the x-intercepts are the points -2, 0 and +2, 0. For the y-intercepts, that's the point where it crosses the y-axis, which is this point right here, which we know is the point 0, 3/2. Now, one thing they didn't ask for, but they could have asked for, is, what are the zeros of f of x? Well, remember, asking what are the zeros of f of x is the same thing as asking where does it cross the x-axis. And you can see that it crosses the x-axis here, and it crosses the x-axis here. So the zeros of f of x are x equals -2 and x equals +2. Right? Those are the values of x that give you a y value of 0. And for our final example here, we just want to answer a question. Which of the following equations describe y as a function of x? So if you want to know if an equation represents y as a function of x, what you need to do is solve for y. It's very helpful to do this. So in the first equation, we have 2x minus y is equal to 1. To solve for y, I'm going to add y to both sides. This will give us 2x is equal to 1 plus y. And then I'll subtract 1 from both sides. And this gives us 2x minus 1 is equal to y. Or I can write this as y equals 2x minus 1. Does this equation represent a function? Okay, what it means is that when you plug in an x value, do you get exactly one y value or do you get more than one y value? So just think about an example. If you plug in x equals 5, y is going to be 2 times 5 minus 1. This is 9. So when I plug in a single value like x equals 5, notice that I'm getting a single value for y. And that's going to happen every single time. So yes, this first equation represents a function. Now what about the second equation? In the second equation, we have the absolute value of y is equal to x. How do you solve for y here? Well, remember the definition tells us that if the absolute value of y is equal to x, then that means that y has to be equal to plus or minus x. That's the definition of an absolute value. So now if, for example, I pick x equals 5, y is going to be positive or negative 5. So what that means is if I pick x equals 5, y is either going to equal 5 or y is going to be equal to negative 5. So if you think about that on a graph, what we're saying here is that when x equals 5, which is this number here, y is equal to 5 or y is equal to negative 5, okay? That is not a function because that fails the vertical line test. If I draw a vertical line right there, I'm going to hit twice, okay? But let me show you more. If you had picked x equals 4, y would be plus or minus 4. If x was 2, y would be plus or minus 2. And finally, if x was 0, y would be 0, right? So if I plot all these points, we have 4, 4, we have 4, negative 4, we have 2, 2, and 2, negative 2, and we have 0, 0. And if you graph this, you can see that what you're getting here is a graph that looks something like this. And you can see very clearly now that if you draw a vertical line, you are going to intersect that graph more than once. So no, this equation does not represent a function.